back over to Rado for the demo.
Yeah, thank you, Jeff. So this is our platform. It is what you're seeing here is the cloud-based version of it, but it can be installed also on premise. And it has various modules from data access, metadata, self-service workbenches, libraries, and dashboards. But I'm going to focus on the self-service workbench and show you the three core functions that make the technology, starting with a motif search and finding similar patterns using a motif search, using correlated searches, which are very important within multidimensional space, and going to really a large-scale search in a highly dimensional data. So let me open here a data set that comes from Turbofans, and that data set is on minutes, and what you see in the user interface is a standard workbench looking very much like Excel or Power BI, but specifically tailored the design to time series data. And because time series data is very huge, we have two sections. One is what you currently see on the screen, and underneath is a navigation that shows you how much of the current data available in your data set can be displayed on the screen. There are limitations on what different screens can display. Some can display 5,000 points, some can display 500,000 points. So we accommodate all of this. And in this case, this is engine data. So let me go, it has several, let me focus on one engine here, type, and we'll focus on one engine type, and we'll show all the engines on the screen. So what you're seeing now is right here, 100 time series. That means one time series per engine. So we have 100 units of engines within this type of engine. Now let's show all of them on the screen. We can't fit them. We're fitting only this small portion. And you can see this kind of compressed time series of engines starting and ending. And next, I'm going to open from the library a motif of normal operations. So very often a test engineer or a reliability engineer, they know what a normal operation is, and they want to start exploring the data and look for this, look what differs from this normal pattern. So I'm going to configure a matching algorithm here. There are a few parameters that are taken off, and I'm going to search within each of the 100 engines that are displayed, and I'm going to look for a worse match. Is there something in this engine that's drastically different from what you are seeing and what you have as a matching operation? And that's a very simple way of us going through, again, large data sets and discovering those that differ. Oops, I had to change one more thing. I want to look not from the top 9, but I want to look through all of the 100. And let me rerun the search. So that's going to execute 100 queries looking through every data and every point in this data set. And what you see here is what we've returned. So let me zoom a little bit on it. And you're seeing at the end that it's identifying the very differences of this from this pattern when the operations actually in real life dropped significantly down. So if we look here, it dropped significantly, a very sharp drop from the normal operation, and therefore this engine has been flagged as something going on or something being irregular. And that's the easiest way that we find many of the test engineers are using, or quality engineers using us to find anomalies that are fairly complex in some cases. I would switch to a slightly different data set to show you a correlated search when we want to find a pattern between two measures that potentially can show exceptions. These are thermal power generators, and we have fans, and they have a pattern in the library defined. This is a correlated pattern, and I'll explain it. And notice here, this data is about 2 years of minute-by-minute data on a single turbine. And notice how little of the data we can fit on the graph. But essentially, this search and this query for a different pattern would go everywhere. So what the pattern means here is that you're seeing a jittery pattern in one, the red lines, in one of the fans, that's followed by a very big spike in the other fan, and that leads to faulty operations. And so we're looking in this case not for anything different, but we're looking for the exact match or a match within parameters. So we want to find a match that's 90% different or expressed in cutting off points that's 90% similar. And so we're going to search for it, and we define it, bring us the top results that you match, and we'll look at the cutoff point. So we are running through a tremendous volume of data on a minute by minute basis. We're taking and breaking it into 106 minutes, the entire data set, traversing every one of them and finding these correlations. What I'm going to do now is I'm going to see here is a match that is nearly 100%, very close on the fourth digit. And you can see that we don't have a second match that's within the 90% limit that we had. So we want to go to that match, that very first match, zoom on it, and then bring the production variable. And as you can see, there is a lot of metrics in this system so that we can see what's happening in the real production process. And as you can see, right after the pattern, there is a significant slow in that production process, which somebody had to interfere to bring down. So again, here we're emphasizing the ability of searching for a correlated pattern. It can be 3, 4, 5 measures that are correlated. The correlations don't need to occur simultaneously. They may be offset in time. Some may occur earlier, some may occur later on it. And we're able to define cutoff points so that you can find patterns that are within certain limits so that you can eliminate any false positives on the pattern. And the third demo that I wanted to show comes actually from a transactional database. This is an Expedia sales of bookings, Expedia. And the question there is, and I'll show two very interesting functions here. The first one being that this is an aggregate data. All the transactions across all properties. And what most people are interested in is to find these spikes and pull them on a property level, on a site level, because they can be indication of good sales or they can be indication of fraud. And so let's pick up this pattern here. You see it now. I selected it right here. And what I'm interested in, this is kind of anomalous purchasing, but I need to have the stable pattern before the anomaly occurred so that I can benchmark and find patterns that have an anomaly. So I need to benchmark mathematically against the normal. And the challenge here is the following, is notice what happens if I introduce the product ID as a dimension. So suddenly we're going to 92,000 properties that are being sold through different sites. And if I add also the store, the website through which Expedia sells, it sells through multiple sites in multiple countries. Now I'm looking at over 940,000 time series. So the challenge here is to pull out of these instantly what that type of patterns. So let's get the algorithm again set to it, the right one for this data, and let's run it. So what I'm doing here, I'm running 900,000 queries simultaneously, and each one of these 900,000 queries goes through a year of transactional history to find the top patterns that match this type of pattern. So I'm going to switch now to a matrix view to visualize my my matches. And as you can see them here, they're fairly close. They're within the bounds of what is happening here in the pattern. And the one thing I wanted to emphasize, that patterns in real life are never identical. They're never 100% the same. This is why the complex math comes into place. So we can accommodate and say that these two patterns are mathematically the same, even though this one has a bump here and this one has a bump here. And that becomes extremely important when we're dealing with very, very large data set. And as a matter of fact, we were talking yesterday with the manufacturers that that's probably the biggest problem for them, is to be able to pull that information out of, some factories have anywhere between 10,000 and 1 million sensors. And being able to pull it out of that, like we showed here, out of nearly a million one, is a scalability really accomplishment. So with this, we're done with the demos. And Jeff, I hand it back to you.